Right, so we've got a worked example here, which is relating to the normal distribution, and it's illustrating, at least the first few parts of it are illustrating the inverse normal function. So this is a function on your calculator. And then it goes on to a nice little example with unknown mean and standard deviation. So this is quite a good example. Let's have a look. The variable x has the distribution normal, mean of 20, and a variance of 9. Remember, this is always the variance in the second parameter. So standard deviation is going to be 3. Find the probability that the random variable is greater than 25. Okay, so this is basically just a normal use of your calculator for the normal distribution. So the probability that the random variable is greater than 25, well, we'll just go to the cumulative normal on our calculator. It's in menu 7, obviously. And we will put in a lower value of 25 because the upper value is everything else to the higher of that, so 4 nines or something like that. Put in the mean and standard deviation of 3 in there. This is going to give us this probability, 0.047824 decimal places. So that's just exercising our use of the normal cumulative distribution. Now, the second part's slightly different. Given that the probability that the random variable is greater than a is equal to 0.2, find a. Okay, so if we just have a look at this little diagram, here we go, a little bell curve, that's the normal distribution. Here's our value a that we're trying to find. What we're saying is that the area to the right of that and under the curve is 0.2. So therefore, everything up to a is going to be 0.8. So again, this is just a function on the calculator. Since we know the mean and the standard deviation, we can go to the inverse normal. That's option 3 in menu 7. And we'll just enter these parameters. Area 0.8. Because the calculator gives us the values up to, so it's a kind of less than or equal to function. So the area is 0.8, mean standard deviation in there, and that's going to give us a value of this 22.5 to etc. etc. So that is the value for which this area is 0.8, and therefore this area to the right is 0.2. See, it's a little bit is similar, but slightly more involved. Find b such that the probability that x lies between 20 plus b and 20 minus b equals 0.5. Well, this is just exercising our kind of how we can flex the normal distribution, and I suppose it's testing our knowledge of the fact that, of course, it's symmetrical. So the area to the right, or so between 20 and 20 plus b, is going to be equal to the area under the curve between 20 minus b and 20. So what that means, therefore, is that, well, this area, we're told that the area underneath is 0.5, that's come straight off the question. So therefore, the area in these two tails, because it's symmetrical, is going to be 0.25. So if we add this tail to this bit in the middle, then the area up to 20 plus b is going to be 0.75. So then we can go back to our calculator. We want the probability that x is less than 20 plus b, being at 0.75, and that's going to give us a value of 20 plus b is going to be 22.0235. You can, I haven't put the screens or use the calculator on this, so you can try this out for yourself if you don't. Yeah. Just want a bit of practice, basically. So B is going to be, well, it's the difference between 20 and this figure of 22.0235. There we go. Right, so that's good. Now this part 2 here, the variable y has the distribution normal mu and a variance of mu squared over 9. So find the probability that y is greater than 1.5 mu. Now, this kind of looks a bit unusual, doesn't it? So, well, the main point here is we cannot use the inverse normal. If we haven't got the mean and standard deviation, we've got nothing to plug into those spaces on the calculator. So this is where we have to we basically have to go back to using the standard normal. So this is kind of another way of just testing on knowledge of the standard normal. So what we're looking at, we want the probability that y is greater than 1.5 mu. Okay. We don't know what mu is. So, right, to look at that a different way, we do know that the standard deviation is mu divided by 3. Yeah. That's what that is there. Square root of this variance. And therefore mu equals 3 sigma, 3 times the standard deviation. So we can do a bit of a substitution here, and this actually helps us. Okay, so we're now looking for the probability that the random variable is greater than the 4.5 times the standard deviation. 4.5 standard deviations from the mean. Okay, so we can convert this to our z random variable. So this is the sort of the converted or the equivalent random variable on the standard normal. So what we do is we subtract the mean, divide by the variance. Okay, so that's our conversion ratio for converting from a random variable to with mean and standard deviation to a standard normal with mean 0 and standard deviation of 1. So well, this works out nicely because basically we're divided by 3 sigma, that's what mu is, then divided by sigma, which is the standard deviation, and all the sigmas go out, and we're basically just looking for the probability that this the standard normal random variable is greater than 1.5. Now we can just use our calculator to do that, and we're going to put in a lower of 1.5, an upper of 4 nines, let's say. We've got standard deviation of 1 and mean of 0 because it's standard normal. Press the button, and that's going to give us this probability here, which to 4 decimal places is 0.0668. Okay, so that's kind of quite an unusual form of question. Just takes a bit of practice, I think, with these things. We've got, a little bit of manipulation with the mean and the standard deviation, but you can see it actually comes out quite simply, really. Okay, so hopefully that has been useful, and I'll see you in the next video.